Hello, everyone. I'm very happy to be here today because I'm going to share with you a low-loss tunable matching network for reconfigurable antennas, but not only. This is about a new RF switch type that enables new technologies, and we are going to showcase that with this array antenna. I'm Marius Patriotis, an alumni today, and this is my awesome team, Dr. Firas Ayub and Dr. Christos Christodoulou. We are together, we innovate to introduce you a new antenna operating concept that is a single antenna driven by a single RF port that can achieve 15 reconfigurable radiation patterns. And not only, also we introduced an RF reconfigurable 4 output port switch, which is able to have the 4 ports independently activated and always in a match condition. Therefore, there is no need for extra expensive antenna sources. Rather, we conclude that in this compact design. Well, background check. Don't take my word, but check it yourself. There has not been yet reported similar performance. Let's take the industry. It has reported a single pole NITRO switches, namely reflective one, which is the diagram we see here, where for this case, Ni takes the number of 2. You have a common port and 2 output ports, where it's called reflective because the inactive port is not terminated. The second topology, it's the absorptive one, where the difference is having the inactive port now terminated to a load. Well, these two type switches have a common thing. The power from our source is delivered only to a single output port. Now let's check the science research or academia focusing on antennas. Well, it has been noticed that they apply common practice of utilizing the industry available switches to achieve pattern configurable antennas. There is also a limited effort to increase this number of patterns, but still with not equal power distribution to each radiator or not with full total independent control from each port. Taking a closer look, an 8-element array has achieved 29 states out of 63 possible. In the other case, there is a 4-element array that achieves 11 states out of 15 possible. In contrary, we are enabling a case where our antenna can achieve the maximum available. Let's say we have a 4-element array, 2 at the power of 4, 16. We exclude the off state. This is 15 reconfigurable patterns. Let's take a look at applications. Of course, wireless communication, which can happen cheaper and with an improved coverage. Why? Because the antenna now can adapt in new varying electromagnetic environments. Moreover, the RF front end can now start thinking of single pole variable throw systems. So far, they had only a single pole and throw. And of course, this can scale to different frequencies. Bottom line, platforms such as CubeSats, Vionics, or vehicles can now perform with more functionality with no cost in size or weight. And also currently, in order for one to achieve similar performance, must go expensive and complex. Let's see what's the market potential. I would like you to think wireless. Wherever wireless exists, then there is room for implementation. That can be CubeSats, drones, 5G networks, telecommunications with their base stations, automotive, radar, even security. And in general, wherever we would like to have fewer antennas and reduce cost. And don't forget, there is a great momentum towards smart cities. Now, let's take a look what I'm talking about by showcasing that with a 4-element QRA antenna, 15 reconfigurable patterns that is designed to meet the next specifications, and being that radiates with circular polarization, fit plane coverage, that means 360 degree at the azimuthal plane, is designed for 10 gigahertz operation, and of course, like minimum losses with a single RF port driven. For our better comprehension, I'm gonna break it into 3 simple design steps, starting with the radiating unit employed in the array. Then I'm gonna talk about the backbone of the design, that is the new switch type. And then last, the combination of the two for the new product. Here we see the design of the radiating unit, where each is composed by 4 rectangular patches truncated and aligned in this configuration to provide us the purest polarization. This consists of 2 parts. On top is the radiating unit, and in bottom is the circuit that drives each element. This is a stack topology, and the reason is we would like to isolate the radiating unit with microwave components, and therefore also to reduce size. And this is how it performs. It radiates with 9 to 10 dBIC with a very low cross polarization, and the graph here below -10, it defines the operating range, which is about 1 gigahertz, but we are focusing at the center frequency of 10. The next design step is the new switch type, which follows again stack topology. I will talk again, in a bit by the reason. This consists of the reconfigurable matching network on top, the reconfigurable switching network in the bottom, and we stack them together. Here is the side view in order to, again, reduce the size, but also to maintain uniformity. We will see what that means. Starting with the reconfigurable matching network, what does that do? We actually enable now tunable factor in our transmission line, which it actually creates a new matching condition for each new case that happens in the bottom. As you can see, the transmission line ends in these vias that connect our switching network. This is a uniform structure, this cross, but what you actually see, it's 4 output ports, P1, P2, 3, and 4, where each transmission line now implements its own tunable element in order to enable this time current to pass or stop. What a better way to explain the concept by an animation. Therefore, here we present the case for activating one arbitrary port. In this case, we choose this one, but it could be any of the other 3. As you follow the current, we have distribution from the input to a single output. Following the graphs that define the operating behavior, the black curve defines the operating frequency, while the red and the other 3 defines the output ports, where for our transmission coefficient, this is called transmission coefficient for the enabled port, while that means it's the current is delivered only to a single port, while the 3 other curves are perfectly aligned. And as we can see, we have an isolation increase more than 23 dB. Here is the phase graph. to show that the current reaches each port at the same phase. Here is the case where we enable 3 arbitrary ports in order to demonstrate the equal power distribution. As you follow the current, it's equally distributed among the 3 active ports, where the inactive, as you can see, no current reaches at it. Taking a closer look at the graphs that describe the operation, here now we have the 3 active ports with the transmission coefficient showing to be active. This while the inactive one has an isolation more than 28 dB, and the black curve is the operating frequency region, which indeed operates at 10 gigahertz. Note that at each port you can actually implement your next circuitry. And the last step is the combination of the two in order to form this new cube antenna structure, which what is new, it's actually the operation. Here we will see how the reconfigurable pattern antenna operates when we enable 1 port, meaning 1 beam. Therefore, we have 4 cases, and this is the 3D, where this plot shows us the operation at 10 gigahertz, which is a little bit actually wider. Next is the case where we choose to activate 2 ports at the same time, where it's the case of 2 adjacent ports or 2 opposite. As you can see, here the beams cover this configuration enables 6 cases with always match condition. In the next cases is 3 and 4 port actives. Therefore, 3 adjacent beams or an omnidirectional antenna, while maintaining an always match condition. And this antenna, this actually device is able to achieve the maximum possible report, the maximum number of reconfigurable patterns. What is our current status? Well, we are conducting further research because we would like to redesign the network for integrated circuits. We would like to see that in a surface as a surface mount component. Also, we would like to connect a microcontroller with some machine learning algorithms to make the antenna more autonomous and more cognitive to the environment. Moreover, we are welcome to extra feedback. We are seeking for that because this will allow us to improve our model. And most importantly, it's our vision where we would like to see that implemented in any by telecommunication companies, government agencies, future trends such as autonomous driving, and would like to offer this design type in order for them to develop or improve their products and innovate with their way. Thank you for your attendance and your attention.